Okay, so like I said about nomenclature, this is what we're going to do today. We're going to get through the first part of nomenclature. And again, I'll reiterate, chemical nomenclature is a central piece of learning chemistry because it's the language we use to talk about elements, atoms, molecules, and compounds. And it just ends up being such a huge portion of the basic and the beginning part of general chemistry. Today, what we're going to do is 4 things. Like I said before, we're going to try it in 4 different phases. There's a total of like 8 or 9 different types of nomenclature to know. And so we're going to work on 4 different pieces of that today, and then we're going to be done. The first piece is going to be straightforward. It's going to be a discussion about the elements on the periodic table, their symbols and their names. And then I'm going to tell you which subset of the elements on the periodic table that I want you to know. The next thing that we're going to do then is talk about the natural states and natural formulas of those elements. Because when we talk about elements on the periodic table, we're just talking about their symbols and their names. It doesn't tell us anything about how we find them in nature. And that's what we're going to do now is for that second phase is to take the information from the periodic table and then be able to apply that into how we find those elements in their natural states. The third thing then we're going to do is we're going to introduce the concept of ions. I know that we've already defined them as far as a species that has a charge, and if it has a positive charge, it's a cation. If it has a negative charge, it's an anion. But what we're going to do is we're going to look at how elements on the periodic table gain or lose electrons to become ions. It happens in a particular pattern, and you can view that pattern on the periodic table of elements. Now, there is a reason why a particular group takes on a particular charge or gains a particular number of electrons or conversely loses a particular number of electrons. But that discussion is really not appropriate at this point in the class. We're going to save that until a little bit later. So for introductory chemistry, that's going to happen way at the end. For general chemistry, that would sort of happen in the middle. And so that's going to be the third thing then, is to use the periodic table to then identify the names and formulas of the ions. Then the final thing that we want to work on, which will be probably the most challenging part of the day, will be to think about the names and formulas of ionic compounds. Ions have charges, positive and negative charges. They're cations and anions. And outside of very special circumstances, they don't essentially exist in isolation. They always exist with a counter ion. So a cation always exists near anion, and anions always exist near cations. You can't have a jar of negatively charged particles on the table. It doesn't work that way. And so what we're going to do is look at this very basic understanding of how we name and develop formulas for the compounds that form from ions. They're called ionic compounds. That introduces a little bit of a challenge because you need to learn a way to predict the formula correctly. And this really does form a foundation for future nomenclature. So the very last thing that we're going to do today really does establish a baseline, as I said, a foundation for moving forward in nomenclature practice. So again, atoms, we're going to learn about elements, their names and symbols. We're going to learn about their natural states and their natural formulas. Then we're going to talk about monatomic ions as we can gather them from the periodic table. And then we're going to talk about ionic compounds. And so let's get back into that then. And I want to take a look at a periodic table of elements. So let me share my screen real quick. So I'm going to shamelessly promote a pretty decent website. I use it quite frequently. I ask my students when we're in a face-to-face class, oftentimes they don't have a periodic table with them. So I say, Hey, jump on over to ptable.org. This will help you sort of get a feel. This will give you a basic idea of having a periodic table available to you almost all the time. So ptable.org, it's just one version of an online periodic table. And so because I can easily share my screen with an online periodic table, I choose ptable.org. Maddie, it's ptable.org. So ptable.org, and you can go to ptable.com. It's the same website. Okay. So let's take a look. I've already asked you to know the name and symbol of the first 30 elements. So that gets you to zinc. So that gets you to zinc. So what do I mean by that? And so let's just select potassium as one of my favorite go-to elements. What I expect you to be able to do is that if I present you with the symbol for potassium, which is K, and then ask you to write the name, you should be able to write potassium. Conversely, if I give you the symbol for if I give you the name beryllium, if I write down the word beryllium and say, write the symbol, I expect you to be able to write BE. Does anybody have any questions about sort of the expectation of how to do nomenclature at this very basic level for the atoms and elements on the periodic table? Yeah, the question is asked, do I want you to know the atomic number? And the answer is no. No. You don't have to know the atomic number. The reason is that it is tradition in chemistry to give you access to a periodic table. Even if I took the atomic numbers off the periodic table, you could recreate the atomic numbers. So we don't take them off. So it's very common to give you a periodic table that has the atomic number, the symbol, and the atomic mass. But that's it. It won't have the name on it. So it will not look like this one. It will not include the name beryllium on it. So I want you to know the first 30. So that gets you to zinc. And so I also want you to know some other ones. And I'm going to leave the periodic table up for now, and then I'm going to transition into the whiteboard. And so I'll have this written down for you, but try to take some notes as we go along. So you have to know the names and symbols of the first 30. This is by memorization. You have to know the names and symbols of the halogens. And so that's also group 17. You have to know the names and symbols of the noble gases. And so that's group 18. You have to know the names and symbols of the alkali metals. So that's group 1. You have to know the names and symbols of the alkali earth metals. So that's group 2. Now, I realize that in each of those groups, group 1, group 2, group 17, and group 18, that there are some of those atoms are in the first 30, so you know them already. And so that means that there's not that many new ones that you have to know so far. I've added about 12. Okay, what else should you know? You should know number 47, which is Ag, that's silver. You should know number 48. That's CD, that's cadmium. You should know 79. That's AU, that's gold. You should know number 80. That's HG, mercury. You should know number 50. SN, which is 10. You should know number 82. PB, that's lead. Let's see. You should know number 94. Pu, plutonium. And number 92, U, uranium. Okay. And so that concludes the list of atoms and elements that you should know by heart. And so I'll switch to the whiteboard so you can see what I wrote down. Okay. So we need to know the first 30, 1 through 30. The particular groups that you have to know, all of them, are groups 1, 2, 17, and 18. Then there are some individual atoms that you have to know. And here they are. Individual elements. Silver, cadmium, gold, mercury, tin, lead, plutonium, and uranium. And just so that I'm making sure to get, so that everybody sees, this is an R. The common question I get is, do I have to spell them correctly? The general answer to that question is yes, you do have to spell them correctly. In introductory chemistry, I do provide a little bit of leeway. So if you spell it incorrectly, but you still phonetically, I can see that you know the name, I generally give you credit in the first exam or two. But by the time we get to the end of the semester, you really do need to be able to spell them correctly. And this is a challenge, especially for someone like me who can't spell anything. So I get that. But I did, in my undergraduate degree, take an upper level course called Inorganic Chemistry, where I had to learn every single element on the periodic table, name and symbol, and spell them absolutely correctly. So I did it once. You can do the first 30 plus these extras. So what I want to do is I just want to pause a beat, and if anybody has any questions they can put in chat, go for it. Yeah, the comment was made. We're going radioactive with those last two. Absolutely. Plutonium and uranium are radioactive elements, or they have a set of radioactive isotopes, and those radioactive isotopes are in a have a substantial percentage of abundance. Any question? Okay, so that concludes phase 1. And so I'm going to leave this up in the corner because it's still going to be relevant to phase 2. what we want to do in phase 2 is take our knowledge of the periodic table sort of to the next level. Phase 1 has us asks us to be able to take a symbol and write a name. Remember, I'm only including the atomic numbers so that you know which ones I want you to know by number. But you don't have to memorize the number. The number is not part of what I'm going to be testing you on. It's just the symbol and the name. The next part is we have to figure out how these things are found in nature, and it really is important that we know their natural formula, and that's what I'm going to use, the word natural formula, to describe this particular difference. And so let me give you an example. I think everybody knows what is the natural formula of oxygen and what state that it's found in. I don't think anyone would be surprised that oxygen is O2 gas. And so what does that mean? This is what I want you to do in order to differentiate between phase 1 and phase 2 of nomenclature. When I talk about something like this, when I say O, whatever phase it's in, I'm going to say oxygen atom. I'm going to use the words oxygen atom. For this one, I'm going to use the word oxygen. And this has a potential to be confusing, because on the same exam and quiz, I'm going to ask you to write the symbols or the names of elements. When I ask you to write the symbols and names of elements, I'm looking for this. O, oxygen. In another section of the exam, I'm going to tell you to write the natural formulas and states of a particular set of elements. And in that case, I might say something like this. Oxygen. And the correct answer in that case would be O2 gas. And so this is going to introduce some confusion. When it's appropriate in language to describe what I'm talking about verbally, I will use the phrase oxygen atom to refer to the phase 1 formula, and I will use the word oxygen to refer to the phase 2 formula and state. So let me give you an example. I may say later on in the course, something like the following. Oxygen and hydrogen form water in a chemical reaction. So it would be your responsibility to say O2 gas plus H2 gas forms water. Maybe I said liquid. Another thing I might say is calcium ion and oxygen ion. That's actually not a good idea. Let's try something different. Let's try, calcium atom and oxygen atom have a redox reaction to form calcium oxide. So this would be the appropriate, maybe that's gaseous, reaction for that. So I would say oxygen atom in the gas phase to refer to that symbol. This one is just oxygen. And so again, all I'm doing at this point is pointing out the difference. In language, I'm going to use the phrase oxygen atom when I'm referring to its elemental symbol and name. When I say oxygen, except in those very limited circumstances when I'm testing you on an exam, I really do mean O2 gas. And so What we need to do now is take this periodic table, the symbols and names that we already know, and talk about how we find them in nature. So oxygen is an example of that. And I think maybe you also know that hydrogen is H2 gas. This is hydrogen. So let's go through this. You have to know the name, the natural formula and state of everything on the periodic table. Now, you only have to know this bit by heart, but given a periodic table and a symbol, you should be able to determine the natural state and formula of that thing. Well, the good news is this is the way I start. Everything on the periodic table of elements is a monatomic solid, except so let's break that down real quick, make sure that we all understand what we're talking about. Monatomic solid. If I go back to O2 gas, how would I describe that? I would describe that as diatomic, 2 atoms. So what I'm saying is that the natural state and formula of oxygen is diatomic, and the state is a gas. So the natural formula and state of the vast majority of things on the periodic table is monatomic solids. So let me give you an example. Gold. The natural formula and state is just Au solid. The element gold in its natural state is found as an atom. The element oxygen in its natural state is found as a molecule. That's the difference here. Okay, so let's go through the exceptions. So the exceptions go like this. And what I want to do is I just want to stop real quick, stop sharing here. Go back to sharing here. And let's talk about the exceptions. By and large, all of the exceptions are here in the nonmetals and the halogens and the noble gases. So most of the exceptions fall in the spot where I'm rotating my mouse cursor. So in the nonmetals and noble gases. There is an exception right here, mercury. So take a look at the periodic table key at the top left-hand side of the periodic table. I'm telling you what things are solids and what things are gases and what things are liquids. I told you that the vast majority of everything on the periodic table is a monatomic solid. And look at all the different black atoms on the periodic table. They represent things that are solids. Now, some of them aren't monatomic, as we'll talk about here in a second with sulfur and phosphorus. But the vast majority of things are, in fact, solid. So you know their natural state. Their natural state is solid. Let's look at the liquids. It's particularly straightforward in the sense that there's only 2. There's only 2 elements on the entire periodic table that are found as liquids. And one of them is in this little realm of exceptions, this little circle of nonmetal exceptions. The other one is mercury. But mercury should be pretty commonly understood as a liquid, right? Mercury thermometers, don't play with the mercury when it spills, it's poisonous, etc., etc., etc. So this should also be somewhat common in your everyday experience, or at least in your not quite everyday experience. Let's look at the gases. Where are the gases? Again, all of the gases, except for one, are right here in this little circle of exceptions. Hydrogen, of course, is a gas. But remember, hydrogen has the properties of both group 1 and group 17. And so sometimes we see hydrogen appear right here next to helium. So that really does conclude the states. And so let me get back to my whiteboard. So what are the gases? Hydrogen is a gas. Nitrogen is a gas. Oxygen is a gas. Fluorine is a gas. Chlorine is a gas. Here's one way that's easy to remember them. What state do you think the noble gases appear as? Anybody want to take a stab at the natural state of the noble gases? Yeah, they're gases. Good guesses. They're gases. So the entirety of group 18 is a gas. The entirety of group 18 is a gas. So that's definitely helps you remember that. And I mean everything: helium, neon, argon, krypton, xenon, and radon. They're all, Og is one of those things that's unknown. Organocin. So once you start getting into the really heavy elements, 104 and above, things really just sort of like, we don't know. We really don't know, because all we can, because first of all, their half-lives, they're very unstable atoms. They don't exist for very long. And when I say very long, I mean sometimes on the order of less than a second when they're made. So we don't know. If organocin was stable, we wouldn't be surprised to find out that it was a gas. But the problem is it just doesn't exist long enough for us to actually figure that out. We can't get a collection of Og because it doesn't exist long enough. It's an interesting subject, but at the end of the day, we think that some of the thing, there will be some heavy elements that might be stable enough for us to isolate for a minute or two. Okay, what else is a gas? Number 1, number 7, number 8, number 9, number 17, and the noble gases. And that's it. That's it. So what are liquids? Only number 35, and which is bromine, and number 80, which is mercury. Yep, so chlorine and fluorine are gases. And in fact, if you look at the periodic table, fluorine is number 9, chlorine is number 17, number 35 is bromine, and then iodine is number 53. And so this would be group 17 as we get down the periodic table. It goes gas, gas, liquid, solid. And so you're seeing that as an atom gets heavier, it's more likely to be found as a solid. So you see this transition from gas to solid in the halogens quite clearly. Okay, so remember that everything on the periodic table is a monatomic solid, except for the gases, 1, 7, 8, 9, 17, group 18, and the liquids, number 35 and number 80. What are the things that are not monatomic? So there are some things that are diatomic. Again, most of them are in the realm of that region of nonmetals where all the exceptions are. So H2 is one exception. O2 is one exception. N2 is another exception. All of the halogens, F2, Cl2, Br2, and I2, they're molecules as well. What else? There's only two other things that you find on the periodic table that are not monatomic. However, they are not diatomic either. And so real quick, I'm going to stop my sharing. Let's go back to the periodic table from ptable.com. And let's take a look at sulfur. Sulfur is one of those species. Sulfur, it doesn't say. I thought it would say. Phosphorus. No, it doesn't say there. Okay, so it's sulfur and phosphorus. Those are the two elements on the periodic table that are not monatomic and are found as that are also not diatomic. What we find is that phosphorus is P4 and sulfur is S8. Sulfur is S8. So let's write those down real quick. And I'm just going to use the word polyatomic to describe them. I'm going to use the word polyatomic to describe them. P4 and S8. So I'm going to shrink that out. And so that's all the exceptions. So again, everything on the periodic table is a monatomic solid except for the following. There are some gases and some liquids, and we talked about which ones those are. And there's some things that aren't monatomic. There's some diatomics and a couple of polyatomics. I don't think I've missed anything, but if I did miss something, let me know. I think I'm okay. Let's see. Just double checking. Yeah, I think I got it all. And so let's kind of put this together. What would be the natural formula and state of these molecules? And so now what I want to go ahead and do, I'm going to write down. This one is H2, right? 7 is nitrogen, N2, oxygen, O2, fluorine, F2, 17, Cl2. Group 18, we already talked about all of those noble gases. We don't need to really do that again. The liquids, this one is bromine, Br2, and then the formula for mercury is Hg. Okay, so how would we put this together? I would say, write the natural formula and state for the following. Here they are. And so I might say something like, again, I'll give you the example. Oxygen. So the question was asked, sulfur and phosphorus are still solid, and that's true. Right? So sulfur is not an exception for its state, it's only an exception for its formula. So O2 gas is an exception on both accounts, but sulfur is only an exception in the fact that it's not monatomic. So it's S8, but still solid. Same thing with phosphorus. P4, solid. What would be another example? Let's say mercury. Mercury is an exception for its state, but not its symbol. Mercury liquid. I think Br2, bromine, is an exception on both cases. It's a diatomic and it's a liquid. So this is what I mean by this. And so by and large, all of the atoms on the periodic table are monatomic solids, but there's some exceptions. Most of the exceptions involve the states, but at the end of the day, you know most of these states. The other exceptions involve the formulas, and I think you know a lot of these formulas as well. If you don't, you can see that they're all pretty much well-oriented around the same sections of the periodic table. Most of all of the exceptions are in the nonmetals, the vast majority of them. Okay, so what I want to do is pause there. That's all of phase 4. So remember, phase 1, just take a symbol from the periodic table and tell me its name. Phase 2 is if I give you a particular element and say what's its natural formula and natural state, you should be able to do this. And of course, all of this is by memory with only the help of a periodic table that has only symbols and atomic numbers on it. No names. So any questions about that? Plutonium is not natural. That's not correct to say that it's not natural. All of these elements are natural in the sense that they have some sort of existence in reality. Some of them are not found in nature. Some of them are synthesized by humans. Plutonium is not one that is synthesized by humans. Plutonium is found naturally. Pretty sure. No, maybe it is. No, I'm not going to say that. Let me just say this, Adi. The question is, is plutonium natural or not? I don't know the answer to that question right off the top of my head. Maybe I should. I definitely know uranium is natural. We definitely have uranium mines. And so maybe plutonium is only made through the decay of other things. But the sheer amount of plutonium that we have in the world, to me, indicates that it is actually a real thing as far as found in nature. But I'm not actually, when I get to this, when I talk about the natural formula and state, I'm not asking you to tell me, is it found in nature? I'm asking you to tell me, what would its natural formula and state be? The question is asked, do they come from the respective planets? And so no is the answer to your question specifically, but the origin of atoms and elements is astronomical. And so I'm not going to do the whole story, but the short answer is this. In the Big Bang, we only created hydrogen, helium, and a little bit of lithium. It took hundreds of thousands of years for stars to form, and then millions of years for those stars to explode in supernovas. While a star is doing its star thing, it's actually powering itself through nuclear fusion. So hydrogen and helium get together, they form heavier and heavier elements, all the way up, I think, until about carbon. Carbon is the common element that's formed in stars. If the star is massive enough, it can form all the way to iron. But iron is the last element that can be formed inside of a star. So remember, Big Bang only gives us 3 elements. The initial formation of stars gets us up to iron, but iron is only number 26. And so how do we get elements beyond that? Well, then stars explode, and the energy of the explosion fuses heavier elements. And so the bottom line is that all those elements that are after iron, including zinc, which is 30, and you have to have zinc in your body in order to live, were made through successive supernovas. And so literally we think about, well, what are we made of? Mostly carbon, and carbon was formed in the heart of stars. It wasn't an element that was automatically in existence with the Big Bang. And in fact, stars had to die and explode in order for you to be here, because without it, we wouldn't have any zinc or other elements that are heavier than iron. And so at the end of the day, it really is true that you're made out of stardust. It's not just a platitude. It's true. But that's all I want to say about that. You can look into that a little bit more deeply. It is pretty interesting where atoms come from. Nuclear synthesis. Nucleosynthesis is the words you want to look for. Okay, so it's almost getting closer to the 10:30, and so what I want to do is kind of move on. Let's talk about phase 3 now. Phase 3 is ions. And what I mean by ions is that atoms can gain or lose electrons. So a sodium atom might lose an electron to become a sodium ion in the gas phase. A chlorine atom, notice this is not its natural formula and state, might gain an electron to become a chloride ion in the gas phase. We could talk about this together, and we can talk about it from its elemental form. We can say that sodium solid and chlorine gas come together and exchange electrons to become sodium chloride, the table salt. And we'll talk a little bit more later about why I'm putting these numbers 2 in front of there. So remember that elements can lose electrons or they can gain electrons. And notice the two reactions that I'm writing. One reaction represents the loss . One represents gaining electrons. So the first reaction represents lost electrons. The second reaction represents gained electrons. And so we haven't talked about reactions yet, but in short, these are reactants. These are products. And when you lose an electron, it's a product of a reaction. When you gain an electron, it's a reactant. Okay, so what I'm going to do is I'm going to stop sharing. Actually, let's go back to this real quick. And so I want to write down just a few elements. Sodium becomes, and I hate to use an arrow like that. I'm going to use an arrow like this to indicate this is not a chemical reaction. Sodium becomes sodium plus. Lithium becomes lithium plus. Beryllium becomes beryllium 2 plus. Fluorine atom becomes fluorine minus. Chlorine becomes chlorine minus. Oxygen becomes O2 minus. Nitrogen becomes N3 minus. So there's one thing that I want to do with this. So I'm giving you an example of some of the things that happen with atoms as they become ions. Remember, in order to become an ion, you must gain or lose an electron. Which ones lost electrons? All of the ones that are positively charged lost electrons. All of the ones that are negatively charged gained electrons. So I want to stop sharing there, and I want to get this particular piece taken care of. Here's my periodic table in my textbook. This is what I ask my students very often. I say, which one of these atoms on the periodic table is an ion? And some of them go, a few of them. Some of them go, Several of them. Ah. And I say, wrong. Which one of the atoms on the periodic table are ions? And the answer is none of them. None of them. The next question I ask is, which atoms and elements on the periodic table can become ions? Which atoms and elements on the periodic table can gain or lose electrons to become ions? And the answer to that question is all of them. All of them. And so what we need is a way to be able to predict what ions they'll become. And so I wrote down a few and I said, here's some sodium, it becomes sodium plus. Here's lithium, it becomes lithium. Beryllium becomes beryllium 2 plus. Fluorine becomes fluorine minus. Chlorine becomes chlorine minus. Oxygen O2 minus. Nitrogen N3 minus. Boy, if you have to memorize what every single element becomes, in other words, how many electrons it's likely to lose or gain, then you're going to be in a challenge. Lucky for you, you don't have to memorize it. Lucky for you, all you have to do is go back to your periodic table of elements, because the position in the periodic table will tell you what the charge is. Okay. So there's first thing I'm going to do, and this is how I describe things on the periodic table. I do 1, 2, speaking of group 1 and group 2, 1, 2, skip a few, group 13. What's the few that I skipped? What are they called again? What is that section of the periodic table? Anybody? 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 What are the few? Group 3 through group 12 that I skipped. Not just metals. They are metals, but a particular type of metals. Transition metals, exactly. Transition metals. Okay, so you can look at the periodic table and you can predict what the formula of an ion will be when it has a loss or gain of electrons. You can predict the formula that an element will take on, and thus the number of electrons it loses or gains based on its position in the periodic table, with the exception of the transition metals. And of course, the lanthanides and actinides as well. You can't predict those. So you can predict group 1, you can predict group 2, you can predict a couple of atoms, boron and aluminum, in group 13. You can predict group 15, group 16, and group 17. And in this course alone, we're going to say that group 14, it just doesn't form, carbon and silicon don't form ions. And then noble gases, will say in every class, they don't form ions. There's just this little thing called the post-transition metals. So they're not metals, right? And they're not metalloids. So here are the metalloids. They're not non-metals, right? So here are the reactive non-metals. Here are the non-reactive. Here are all of the non-metals. This is really cool in the way it's highlighting things. They're not metalloids, they're post-transition metals. And these particular metals can form ions, but they're not predictable. It's not that transition metals can't form ions, it's just that they're not predictable. In fact, they form multiple different types of ions. And so we'll talk about that here in just a second. So how do we predict things? Group 1 will always form +1 cations. Group 2 will always form +2 cations. So that's 1, 2, skip a few. We're at group 13. And what I mean by group 13, I really only mean boron. And usually we throw aluminum in the mix as well. So boron and aluminum will do +3 cations. Then group 14, and really we only mean silicon and carbon. They don't form ions. In this course, it doesn't mean that they don't actually in real life form ions. It just means in this course they don't. Then we get to group 15. -3. Group 16, -2. And I don't want to squeeze it at the bottom, but group 17 is -1. And these are all anions. So let's go back real quick. Let's go back to so how does it work? So think about this for a second. It is a fairly straightforward pattern. Group 1 is +1. Group 2 is +2. Group 13 is +3. So 1, 2, 3. Group 14 is the 0 mark. We're going to say they don't form ions. Then we're going to go back the other way and we're just going to switch the sign. So 1, 2, +3. Then group 15 is -3, -2, -1. So that's how you're going to predict the formulas of these different ions. What about the formula of transition metals or other things that can't be predicted, like lead? Well, lead and other things that can't be predicted, like iron, will actually have multiple ions that can form. Iron can be 2+, or it could be 3+. Here's the thing that you will know about the transition metals and the post-transition metals. They will always form cations. All unpredictable species form cations. So you don't have to worry about any unpredictable anions. Okay, so let me give you another example. So lead, Pb, can form an ion that's 2+, or it can form 4+. And some transition metals have quite a few different ions that can form. I think molybdenum can be +2, +3, +4, etc. All right, so I don't think we're going to get to phase 4. And so let's not worry about that for the day. But let's finish up phase 3. We've talked about the formulas. We can predict that O becomes O2 minus, and we can predict that calcium becomes 2+, a cation. We can predict that sodium becomes Na+. We can predict, or we can't predict, but we can, if I tell you that iron can form Fe2+ and Fe3+, we're not surprised about that. We know that it will be a cation. We just don't know which charges it'll take. But what we don't know yet is how to name them. We don't know how to name them yet. And so let's name them. So this is how we name monatomic ions. So it's really quite straightforward. For cations, we do this. Atom name plus the word ion. So these are actually predictable. Predictable cations. Atom name plus the word ion. Example. Here's a predictable cation. What's its name? Its name is sodium ion. Here's another predictable cation, Ca2+. What's its name? Calcium ion. What about unpredictable cations? Like this one or this one? Well, it's a similar pattern, but because iron can take on more than one charge, we have to be able to come up with a name that tells the reader which one we're talking about. So the way that this one works is we use atom name, Roman numeral, and then the word ion. And the Roman numeral that we use corresponds to the charge of the ion. So this one is iron 2 ion. And specifically, what I want to make sure that I'm telling you is there is actually not a space between here. So it's iron 2 ion, and it's iron 3 ion. And so the next one would be, real quick, what's the formula for this? This is the lead 4 ion. So the formula would be Pb4+. Okay, there are no unpredictable anions, right? Because all of the things that are unpredictable are cations. So monatomic anions are like this. It's the atom root plus IDE. So what's this thing called? Excuse me, O2 minus. This is oxide. What's this called? This is nitride. What's the formula for chloride? Well, let's break it down. This is the ion that forms from chlorine. We know that it has an IDE suffix, so that it should be a negatively charged ion. How do we sort out the charge? Well, we look at the periodic table. We find that it's in group 17, and we know that group 17 forms -1 ions. And so the formula for chloride is Cl-. What about phosphide? Well, the root is from phosphorus, P. So it starts off with a P. We know that it's an ion, IDE. So what group is phosphorus in? It's in group 15. Group 15 forms 3- ions. So we know the formula for phosphide is P3-. Okay, and so what I'm